Hello. For this video, I want to talk about how to implement stacking using R packages. And this is another video in our series in machine learning using R. So in this video, I want to talk about workflow for stacking using caretEnsemble and SuperLearner, the two R packages for stacking machine learning models. So the workflow is step one, fitting the base learners, for example, random forest, GBM, and a linear model. Step two is computing out-of-fold OOF RMSE, the prediction accuracy of each base learner. Step three, computing correlations of OOF predictions. And this is for model diversity. Okay? And step four, stacking using caretEnsemble. Step five, stacking using SuperLearner. And step six, compare accuracies of all models. Okay, let's get started. Create a data set, split them into training and test data set. And then we load in caret and caretEnsemble, that random seed, we get control, we get cross-validation, 5-fold cross-validation, and save prediction for the final model. Then we can specify the model with the caret list. The first one is y regress on all the variables from the training data set using the control parameters. And now we get a tone list. And you got RF, the random forest, we get a caret model spec. We use the package ranger. And the tone grade, we use expand.grade. And we try M tries 2 and 3. Split rule is a variance. And the minimum node size is 5 to 10. Okay. And importance, we use impurity. For the GBM, the gradient boosting machine, we specify this method equal to GBM. Tone grade is expand.grade. Number of trees is 100, 300. Number of bootstrap samples. Interaction depth 1 to 3. And shrinkage is 0.5 and 0.1. Number of minimum observations in node is 10. Verbals equal to false. And for linear model, it's very easy. Just caret model spec, the method equal to LM. There's no hyperparameters. Okay. As you can see, using the caret model, the caretEnsemble, we can actually do some hyperparameter toning here by when we specify the models here. Okay. You can include some grid search in here. If your grid is very, very detailed, it's going to increase computation time. And so there's a trade-off you have to balance. Okay. We can write a function to calculate the RMSE. And now we can write a function. No, we can apply this RMSE function on all the models and the prediction for all the models. And then we can print out the OOF RMSE of each and every base learner. Okay. So that's the first step. And the second step is correlations of OOF predictions. This is for model diversity. So when we do stacking, we kind of combining heterogeneous models or learners. And they are applied on the same data set. So the prediction they generate may be correlated. And we have a large selection of machine learning models. For example, the tree-based model, like the random forest is tree-based, but it's using bagging. And we have the gradient boosting machine, so it's a tree-based and it's using boosting. And we have the very general, very just usual linear model, the linear regression model. Okay, but just keep in mind they are fitted. They're using the same training data set. So because of the data set used and also the internal mechanism of the different machine learning models, their predictions may be correlated. So that's why we want to examine the correlations. And also, we want to make sure we have enough diversity in the model so that we're not having like redundancies, in the model. Okay. So here, just for this example, let's do the predictions, and then we calculate the correlation matrix. Well, and for this example, the predictions from the 3 base learners are highly correlated. The correlation coefficients 0.98 and 0.95, 0.94. So there's a collinearity among these predictions. And this prediction from the base learner will become the input to the meta learner later on. So we will have collinearity from the prediction from the base learner. Okay. All right. So that's why when we do stacking, we want to use regularized learner that kind of reduce the effect of collinearity. Okay. So for using the caretEnsemble, we can just use the function caretStack, and the syntax is you got the models, and this method equal to glmnet. So glmnet is we're using elastic net, which is a regularized machine learning tool. So this is appropriate here because we have higher correlated predictions from base learners. And then we can use the train control method cross-validation, number equal to 5, so 5 votes. And it fits very quickly. And then we can generate the random forest prediction, GBM prediction, linear model prediction, and we combine them into a data frame, and then we can predict, using the final model on the test data set. Okay, not test data, sorry, on the stack input. So the meta learner uses the prediction from the base learner as input. Okay, so then we can calculate, the caretStack RMSE, and we can also use the SuperLearner. The syntax is here. You can see the sl.library is sl.lm, sl.render, and .sl.gbm. A method is NNSLS, non-negative stacking weights. That's the method built into SuperLearner to calculate the weights when doing the stacking. Okay. And this will take some time here. Okay, I actually have to wait a couple minutes for this stacking by using SuperLearner to finish its job. And now it's done. And the next we can generate a prediction using the final model here, and then we can print out its RMSE. And if we're really going to compare all models on the test data set, we can just put all the RMSE together, print them out here. You can see, yeah, you can see actually looks like the SuperLearner, the RMSE is slightly higher than the GBM RMSE, and this is possible because of the meta-learner in SuperLearner was using its own algorithm, and if you have some base learners, you know, they are collinear or there's some other issues, it may happen that the meta-learner, the stack model actually is not more accurate than each individual one. Okay, but you can see the caret stack has a slightly lower RMSE than the GBM. Okay, so you can see in this example, we have seen the models, they are not very diverse. So they gave pretty similar prediction on the same data set. So that's why we use the elastic net, the regularized meta-learner. And for the caret stack, we did achieve a lower RMSE than all the individual base learners. Okay. So that's something you want to see when you do stacking. When you stack all the model together, you get a more accurate model. Okay. And some more words on the comparison of caretEnsemble and SuperLearner. SuperLearner is easier to use because you can just use the default. It does not let you to have like hyperparameter toning. So it's just run, you know, using the default. That's why it may be less accurate than the caretEnsemble. In caretEnsemble, you have some ability to specify how do you do the grid search, you know, do some hyperparameter toning. So that's why you can get a better result using caretEnsemble. But SuperLearner is easier to use. So the selection of base learners, you have large selection of possible base learners, and you want to examine their collinearity, and if they are diverse, less correlated, and you have large sample size, then probably you know you can just use like linear regression or logistic regression. But if you have like a nonlinear effects, nonlinear interactions, smaller sample size, a lot of mixed like categorical predictors versus continuous predictors, a lot of issues with the data, then you probably want a diverse pool of base learners, and also you may want to use, with high dimensional data, you may want to use a regularized meta-learner. Okay, so but you can see it's open for many possibilities. So hyperparameter toning become really important, and we're going to talk about it in the future. There are some R tools, for example, MLR3, which offers automatic hyperparameter toning, so that you can let R find the best stacking model you can find. Okay. So stacking is pretty exciting with the hope that maybe by choosing the right combination, you will achieve a much higher accuracy for learning. All right, thanks for watching, and appreciate your time, and please support our channel by subscribing, liking our videos, and sharing our video with others. Thank you.